Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thank you for joining us today. I'm your host, Henry Regis, and running the technical side of our program are Noah Newman and Zach Schwalbe. We're coming to you live from the Colorado Climate Center here at Colorado State University in, looks like partly cloudy, Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we'll be recording it for future viewing on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, today's webinar, we're going to explore tsunami science and tsunami warning systems. And we're really excited to have with us today is Stuart Weinstein. Stuart is the Deputy Director of the Pacific Tsunami Warning Center in Eva Beach, Hawaii. He has held this position since 2005 and has been with the Pacific Tsunami Warning Center since 1998. He oversees the day-to-day operations of the Warning Center and conducts tsunami training with the International Tsunami Information Center based in Hawaii. A little background, Stuart was born and raised in New York and holds degrees from Binghamton University, Northwestern University, and Johns Hopkins University, where he received his Ph.D. in 1991. He furthered his research with a National Science Foundation postdoctoral fellow and Earth Sciences grant at the University of Michigan in 1991 and at the University of Hawaii as a School of Ocean and Earth Science Technology's Young Investigator in 1993. Well, Stuart yearned for his native homeland of New York and moved back to New York in 1996, where he worked for Bloomberg LP in New York City writing software to analyze mortgage-backed securities. But then Stuart decided he missed the year-round pleasant climate of Hawaii, and I don't blame him for that, and he moved back there and has worked at the Pacific Tsunami Warning Center ever since. Well, Stuart, welcome. It's a real pleasure to have you with us today. Thank you for taking the time out to be with us. And I got a quick question as we start off. How did you become interested in tsunamis? Not everybody goes into that field.
Well, I first became interested in tsunamis, when I was in Hawaii. A few weeks after I moved to Hawaii, there was actually a tsunami warning issued to the state of Hawaii. It occurred, I think it was in January of 1994, and the sirens went off about 6 in the morning, and I had just recently moved from Michigan, where I finished my postdoc in Michigan. And when the sirens go off in the middle of the night in January in Michigan, it means move your car, because the snowplow is coming down the street, and if you don't move your car, you're going to spend the whole morning digging your car out. So given I was now in Hawaii, I knew that was not the case. And so I was very suspicious that, really, a tsunami warning? So I turned on the radio, and sure enough, a tsunami warning was in progress, and that was my introduction to tsunamis.
Wow. Wow.
Yeah. So I was working in New York City, as you mentioned, and then when a position opened up in the Warning Center, I said, okay, the tsunamis are pretty interesting, and this is my ticket back to Hawaii. So I've been here for the last 17 years.
What a great job to have. That's really interesting. Well, we're going to let you take it away with your presentation, and you just click on those buttons there. We'll be ready to go.
Okay. Well, I'd like to thank Henry for the invitation to give the webinar today. My webinar is titled Tsunami Science and Tsunami Warning Systems. Before proceeding, I'd like to thank my colleagues Nathan Becker and Dylan Wong for their invaluable assistance in putting together this talk.
Stuart, this is Noah. I'm sorry. Right before you start here, on your GoToMeeting control panel, under your Show My Screen, if you can click on, it'll give you an option to show your clean screen, and that way we won't see your Start menu below your PowerPoint presentation. So that way we'll get the full screen.
Where do you want me to click on that?
So on your GoToMeeting control panel, if you can open up the red arrow and just underneath the play button, there you should have a drop-down menu under Show My Screen.
Oh, clean. Okay, got it.
There we go. Thank you.
All right.
Perfect. Yep. Looks better. Thank you.
Okay. Well, let's proceed. So I'll start with an outline. First I'll talk about tsunami warning systems in general, and then we'll move to some tsunami science. I'll talk a little bit about seismology, sea level monitoring, tsunami forecasting. I'll present a simulation or two, and I'll certainly have time to entertain questions. So first off, the tsunami warning system. The tsunami warning system is comprised of basically three components. The first component are the tsunami warning centers themselves. They are the tripwire. It's their job is to detect earthquakes, locate them, size them up as rapidly as possible, and figure out what their tsunami generation potential is and issue message products based on the likely severity of the tsunami. Those products are received by disaster management organizations, and they form the second component. And these disaster management organizations can exist on national scales like FEMA or state and local scales like state civil defense agencies. They have it's their responsibility to figure out what sort of hazard mitigation steps need to be taken. For example, they draft evacuation zones. They determine how the population is supposed to be mobilized. And it's also their job to alert the public when necessary. And the last component in the tsunami warning system is public awareness. The public needs to be educated about the particular hazards that may affect them. And in our particular case today, we're going to talk about tsunamis. And so the public needs to understand whether or not they live in an inundation zone. That is, if this is a coastal area that's likely to be affected by tsunamis, and if so, they need to have an understanding of what they're supposed to do when that siren goes off. They're supposed to know where they're supposed to evacuate to and how they're supposed to get there. The time to understand that is not when the siren goes off, but you're supposed to have this awareness beforehand. So just to recap, again, the first component of the tsunami warning centers, their job is to detect earthquake and evaluate tsunami potential. Look for sea level changes. It's their job to monitor the tsunami as it's in progress and issue message products. The disaster management organizations, they receive the warning center message products, and it's their task to develop the hazard mitigation strategies, such as designing, preparing the evacuation shelters, and figuring out how the population is supposed to get to the shelters. And it's also their job to alert the public when the time comes. And finally, public awareness. The public should know what to do in the event of a tsunami emergency. So in some sense, there's a shared responsibility between public and government. Government is supposed to make all the information available, and the public really needs to digest it and understand what is expected of it. And so the duty scientists at PTWC conduct a lot of outreach around the year, but in particular, the month of April in Hawaii is designated as Tsunami Awareness Month. And for that month, there's a whole lot of information that's broadcast on the TV, on the radios, and we give lots of talks to increase public awareness, explain to them where they can get information, how they can figure out whether or not they live in an inundation zone, where they're supposed to go, and what they're supposed to do. So, now back in 2004, and particularly late 2004, a great earthquake started off the coast of northern Sumatra and propagated northward for about 1,200 kilometers. This was the largest earthquake in 40 years, and it generated a tsunami that killed over 230,000 people. 60,000 of those people were killed outside of Sumatra itself, away from Indonesia. Unfortunately, that earthquake occurred in the Indian Ocean, where there was no tsunami warning system. In 2004, the only tsunami warning systems in existence were in the Pacific Basin. And the Pacific Tsunami Warning Center was and still is the hub of that warning system. Regional centers exist in Alaska. The Alaska Tsunami Warning Center, now known as the National Warning Center, had jurisdiction for the west coast of Canada and the United States. And the Japan Meteorological Agency served for the coastlines of Japan. And that was it. Now, as a result of the Sumatra disaster, if we fast forward today, we find that, in fact, most coastlines around the world are covered by one tsunami warning system or another. There is now a tsunami warning system in the Indian Ocean. There's one in the Caribbean. There's one in the Northeast Atlantic. There's one in the Mediterranean. So, in fact, most coastlines fall under the jurisdiction of one tsunami warning center or another, and or should I say one tsunami warning system or another, and that represents true progress. Now, for tsunami warning, there are three basic needs. One, we have to do very rapid earthquake evaluation, right? We want to locate and size up that earthquake as quickly as possible. In order to do that, we need a global seismographic network. Now, it's not just one network, it's actually dozens of networks that we have access to. So a lot of countries maintain their own seismic network and they make that data available to us. We also want to rapidly detect and size up any tsunami that's generated. So we need rapid sea level evaluation. In order to do that, well, we need a global sea level network. And so a lot of countries maintain their own sea level networks, and they make that data available to us as well. In order to bring in all this information to the warning centers, we need very reliable communications. We need reliable communications, not just to grab all of that data, but we need reliable communications so we can send out our message products. It does us no good if we evaluate everything, but our messaging circuits go dead. So we need very robust and redundant communications. All these elements are required if you want to have a timely warning. The word tsunami itself is Japanese for harbor wave. And the Japanese have long noticed that tsunamis tend to be more destructive when they occur in certain harbors than in other places. This has to do with the resonance that takes place in harbors. So if the period of the tsunami matches the resonant period of the harbor, you can have a very destructive tsunami. It will enhance the destructive aspects of the tsunami. I want to point out that tsunamis have no connection whatsoever with tides. Please do not refer to it as a tidal wave. If you learn nothing else today, you will learn that you will not call a tsunami a tidal wave. Tides are the results of the gravitational attraction of the sun and moon, and they have nothing to do with earthquakes or any other mechanism that generates tsunami. Now, tsunamis are a series of waves that may last for hours. So once a harbor or a coastline is affected by the tsunami, those effects may linger for many hours, and the first wave may not be the largest. Now, a tsunami can be generated by any sudden displacement of the water column. So physicists would tell you that a tsunami is a series of long-period waves created by an abrupt displacement of the ocean. And the chief cause of tsunamis are earthquakes. More than 70% of all tsunamis are generated by earthquakes. Next up are landslides, submarine landslides. If you have a large body of rocks sliding under the ocean, that can also displace the water column fairly rapidly and generate a tsunami. Now, sometimes you can have very strong earthquakes that trigger landslides, so you'll have both of these mechanisms operating simultaneously. Volcanoes. Submarine volcanic explosions can generate tsunamis. Perhaps the archetype example of that is Krakatoa, which exploded in the 1880s and generated a massive tsunami that affected southern Sumatra and Java. Now, there are also tsunamis that can be generated by atmospheric phenomena. These are known as meteotsunamis. The one struck the U.S. East Coast in June of 2013, and that tsunami injured 12 people. And I'll talk a little bit more about that towards the end of this talk when I present a simulation of that tsunami. Now, in the NGDC database, the National Geophysical Data Center database, about 11% of known tsunamis do not have a cause. We're not sure what produced them. So how does an earthquake, particularly how does a subduction zone earthquake, or also known as a thrust earthquake, make a tsunami? Conceptually, this is fairly simple. If you consider the situation that we have off the northwest coast of the United States, where the Pacific plate is subducting back into the Earth's interior beneath North America. And along the boundary with the North American plate, this is what we call the fault boundary. The fault boundary is very rough, and effectively the North American plate is welded to the Pacific plate at this interface. But as the Pacific plate subducts into the Earth's interior, moves back into the Earth's interior, it's going to drag the North American plate downwards, causing it to flex, and as a result, that's going to increase the stress along this boundary. And that stress is going to increase until the point where the strength of the rock can no longer support the stress. And at that point, you're going to have an earthquake. And so when that earthquake happens, the North American plate snaps back up very rapidly, and the water of the Pacific Ocean that's on top is pushed upwards. And so initially after the earthquake you have this mound of water that then collapses and sets off a series of traveling waves that we call tsunamis. So how a tsunami is generated by an earthquake is conceptually fairly simple. So let's talk about what I refer to as the tsunami warning premise. We know that most tsunami-genic earthquakes occur in subduction zones, that is the ocean deeps. And in fact, the Pacific Basin has the distinction, unfortunate or otherwise, of being ringed by subduction zones, and hence the popular literature refers to the Pacific Basin, or the perimeter of the Pacific Basin, as the Ring of Fire. And emergency managers in the Ring of Fire have their hands full. They have to prepare for hazards due to earthquakes, tsunamis, volcanic explosions, all sorts of things, in addition to any weather hazards, like typhoons or hurricanes. So the good news is that most, as I stated earlier, most tsunamis are generated by earthquakes. And you're thinking, why is this good news? Well, it's good news because earthquakes can be detected fairly rapidly. Seismic waves travel 30 times faster than tsunami waves. And therefore, it's possible to warn for a tsunami well ahead of its arrival. So this difference in speed between seismic waves and tsunami waves is really what is the linchpin of the tsunami warning system. We can make use of the fact that tsunami waves travel so much faster than tsunamis. So let's talk about wavelength and speed of tsunami waves, or long waves. Long waves are what we call waves where the wavelength of the wave is much greater than the water depth. And if that's the case, if you're dealing with long waves, then the velocity follows a very simple formula. That formula is the square root of gh, where g is the acceleration of gravity and h is the thickness of the water column in meters. Now, the oceans contain waves on many different scales. On the smallest scales, we have the ripples, or capillary waves, and they may have wavelengths, and by wavelength I mean the distance between successive crests of the wave. And the wavelength for ripples may be anywhere from millimeters to inches. On much larger scales, we have the ocean swells, which may have dimensions in the order of a few hundred feet. And if you're out fishing or sailing in a nearshore environment, you can blame the ocean swells for making you seasick. On even larger scales, on the dimensions of hundreds of miles, we have the tsunamis. And given that the ocean depth is at most, 10 miles, several miles deep, tsunamis certainly can be characterized as long waves. Now, as I just told you, that the speed of a wave of the tsunami depends on the ocean depth. And in deep water, the tsunami may be traveling at hundreds of miles an hour. So in fact, if a jetliner took off from Narita Airport in Tokyo, at the same time the Japan earthquake struck in 2011, it would arrive in Honolulu at about the same time as the tsunami. The tsunamis in deep water will travel with the speed of a jetliner. Now, as they get into shallow water, they begin to slow down. The other thing I'd like to point out is that in deep water, tsunamis are not destructive. The amplitude of a tsunami in deep water, even for something as monstrous as the Sumatra tsunami or the Tohoku tsunami, was maybe 1 to 2 meters in deep water. Now, keep in mind, that's going to be spread over a wavelength of several hundred miles. So if you were on a ship in the middle of the Indian Ocean or the Pacific Ocean when either the Sumatra or Japan tsunamis passed under you, your ship would move up and down by about a meter over the course of about 40 minutes or so. That's an acceleration that you're not going to feel. And as a result, one of the safest places to be during a tsunami is in very deep water. However, the situation changes as the tsunami approaches shallow water. It has to slow down according to physics. And so if you consider what happens as the tsunami wave approaches the nearshore environment, the leading edge of that wave is going to start interacting with the shallow water, and it's going to have to start to slow down. Meanwhile, the trailing edge of this wave is still in somewhat deep water, and it's traveling a little faster. Well, what happens is the wave starts to compress. Its wavelength decreases. And the energy contained in the wave, however, is still more or less staying the same. So what's changing has to give is that the amplitude has to increase. So as the wavelength decreases, the amplitude is increasing. And so what is non-destructive in deep water, when that tsunami enters the shallow water environment, the amplitudes can greatly increase. And so what may only be a few tenths of centimeter in very deep water, by the time it crashes on shore, it could be many meters and be very destructive. Another couple of things to characterize waves and tsunamis in general is the concept of the wave height. We refer to the wave height as the peak to trough distance between the peak and trough of the wave. We refer to that as the wave height. And the period, that is the time elapsed between successive crests of the waves. And so tsunamis travel very rapidly. They can travel at the speed of a jetliner. Their periods in open ocean can be on the order of tens of minutes to sometimes even exceeding an hour. Now, we also have a couple of terms we use to describe the effects of the tsunami when it arrives on land. And one of those terms is run-up, which basically tells us how high above sea level did the tsunami get. And inundation, how far inland the water got. And we like to measure these two quantities for any tsunami that occurs because we can use this to test our numerical models. It provides data for testing our numerical models and also allows us to characterize the destructiveness of the tsunami. And you can see here along the beach that all the vegetation is scoured off the beach. And so our survey team will be walking around this debris line here right at the edge and using a GPS instrument, mark the location of this debris line, and that's how we determine the run-up and inundation. So a lot has changed over the years since I've been working at PTWC. In 1999, we were lucky we were receiving data from about 24 seismic stations from around the Pacific. That was back in 1999. Things improved. By 2005 or so, it was probably more than 100 instruments. But today, we are now receiving from almost 600 stations in real time. So the amount of seismic data we are receiving has grown by leaps and bounds. And that has attended benefits. The more seismic instruments you have, the quicker you're going to know about an earthquake, the faster you're going to be able to locate it, the faster you're going to assign its magnitude, the faster you're going to be able to determine what its tsunami potential is. And as a result, the time it takes us to issue an official message product has decreased dramatically. When I first started in 1998, if we issued a bulletin our initial bulletin in about 45 minutes after the earthquake, we were doing good. Today, we're typically issuing our bulletins between 6 and 7 minutes after the earthquake. So more instruments definitely helps. So let's talk a little bit about seismology. There are two basic types of waves. They're also called body waves. These are the P and S waves. P stands for primary, S for secondary. These are the first two. The P is the first wave that you see in a seismogram, and hence it was called by the early seismologists the primary wave because it was the first wave. And essentially the P wave is nothing more than a sound wave that's passing through rock. And a sound wave causes alternating compression and rarefaction of the medium, and it's a longitudinal wave. The shear wave, on the other hand, obeys different physics, and it is essentially the propagation of a shear or a distortion in the medium. And the shear wave is the transverse wave. Shear waves do not exist in fluids, neither fluids or gases, and hence they cannot propagate in those. And shear waves can only exist, therefore, in a solid medium. Now, the shear wave propagates slower than the P wave. The P wave may propagate through the earth at speeds ranging from 6 to 14 kilometers per second, and the shear wave is maybe about 60% of that. And seismologists long ago realized that they could make use of that to figure out how you can locate an earthquake. And I'll talk about that in a minute, but I first wanted to mention another class of seismic waves known as surface waves. They don't travel through the earth. They have to travel along the Earth's perimeter. And surface waves travel along the Earth's surface at speeds of about 3 kilometers a second, and this is much slower than either the S or the P wave. And they have to take the long route. That is, they can't go through the Earth's interior. They have to go through the surface. And their propagation is much more complicated than either the P or the S wave. Now, the early seismologists recognized the P and S waves fairly early on, and they realized that they can make use of the fact that the P and S waves travel at different speeds. the difference, the time elapsed between the arrival and the P and S waves can be converted to a distance. And so this is analogous to using the elapsed time between a lightning stroke and the thunderclap to compute how far you are away from the lightning. In this case, the P wave is the lightning and the S wave is the thunderclap. And so by the 1930s, seismologists had already figured out basically this S minus P curve. And so this shows you the S minus P interval as a function of distance in terms of geocentric angle. And you'll notice this curve bends over to the right a little bit. That's because as the P wave travels to further distances, it actually travels through deeper sections of the Earth and moves faster. So these body waves, actually, the mean speed of these body waves actually increases a little bit with distance. But anyway, by the late 30s, seismologists had fairly reliable travel time charts like this. And so if you know the location of the seismometers, and let's say we had an earthquake in the central United States, and the P and S interval was determined on a seismometer in Charleston, Detroit, and Minneapolis, we can draw these circles that correspond to the epicentral angle associated with that S minus P interval, and where all these circles intersect, that has to be the location of the earthquake. And this can be done mathematically on a computer. Now, once we know where the earthquake occurred and we know how far the stations are from it, we can then actually try to calculate the magnitude. And there are a number of different methods that are used to calculate the magnitude. And all these simple methods, the first one is the local magnitude here, ML. This is the original magnitude scale developed by the famous Charles Richter. It is actually the Richter scale, although the popular media refers to just about every magnitude scale as the Richter scale. But basically, these three magnitude scales, the one here at ML, the body wave magnitude, which is based on the size of the teleseismic P waves. By teleseismic, I mean more than 1,000 kilometers away from where the earthquake occurred. And the MS, which is based on the surface waves. Basically, what you're doing here for each of these different methods, you're picking out a particular wave from the seismogram that satisfies some of these criteria. That is it in the right period range? Is it like, for example, if you're doing an MB, you want to pick a wave that has a period in the range of 1 to 5 seconds, and then you apply this formula. And this basic formula applies to all these types of methods, where you're measuring the amplitude of this wave and its period, and it's, as you can see here, it's logarithmic. And then there are all these corrections that are involved. So it's actually a fairly simple method to use. But however, as simple as it is, keep in mind that it is just based on one wave. And so it's like trying to figure out what the size of a pizza is just by looking at one crumb. It's amazing that they do as well as they do. The problem is, for the really great earthquakes, these measures, which just look at one wave, don't work out so well once the magnitude of the earthquake gets above an 8 or so. And so we use something called the P-wave moment magnitude method, or the NWP method. And it may be a little hard to see, but if you look down here, you'll see a trace of the seismogram. And in fact, this method is based on looking at a section of seismogram rather than an individual wave. And the blue curve here is the energy release of the earthquake as determined from the seismogram. And then the green curve here is the magnitude, and we choose the magnitude at the largest peak. And for this earthquake here, it was just a 7.2. But for the Sumatra earthquake of 2012, here the magnitude was about an 8.5, 8.6. And those traditional measures, the MB, MS, would not have given us as good a magnitude as we get from the NWP. So there's a lot of value in looking at a section of seismogram. One thing you can also gather when you look at a section of seismogram is you can get a very reliable indication of the fault geometry. And so we can determine how the fault ruptured from the seismograms too. And so there are three basic types of faults. There are the strike-slip faults, where the ground moves horizontal. That's an example of that is the San Andreas fault. And strike-slip faults can occur under the ocean too. In fact, that Sumatra earthquake in 2012 that I just talked about was in fact a strike-slip fault, which was good, because if the ground is just moving horizontally, it's not going to displace much water. On the other hand, if you look at the thrust or normal faults, here the ground is basically moving up or down. And so if a thrust or normal fault occurs under the ocean, it's going to displace the ocean up or down, and that can generate a tsunami. So the key things we can get from the seismograms, we can locate the earthquake, we can size it up, and we can determine what the fault geometry is. Now, before moving on, I want to say something about the earthquake magnitude. People ask me, well, this earthquake was a 7 and the other one was a 6, and, really, 6, 7 doesn't sound like much of a difference, Stu. Really, what's going on here? Well, the magnitude, if you look at this formula, remember, it's a logarithmic scale. And in fact, the energy released by the earthquake is super logarithmic. So for each unit difference in earthquake magnitude, the energy difference is about a factor of 32. So a Richter, even I fall into that habit. So an earthquake with a magnitude of 7 it releases approximately 1,000 times the energy as an earthquake with a magnitude of 5. So let's play this perspective that was developed by Nathan Becker to help put these things, the difference in earthquake magnitude, in perspective. We'll get going in just a minute. Okay, so let's start with the Virginia earthquake in 2011. This shook up most of the East Coast, and people thought this earthquake was pretty big, but in fact it was just a 5.8. So the circle here is scaled to the energy release of the earthquake. Now the 7.0 that occurred in Haiti basically destroyed the capital city of Haiti, Port-au-Prince, and unfortunately killed 200,000 people. That was a 7. People think that's a really big earthquake. Well, the next earthquake to come up is the Mentawai earthquake, which occurred off Sumatra in 2010. And I'll stop it here. The Mentawai earthquake was approximately 2 magnitude units greater than Virginia, and as a result, it released approximately 1,000 times the energy. Now, if I fast forward this perspective here to getting closer to the end, you can see now that even the 7.0 Haiti earthquake has all but disappeared compared to the greatest earthquakes that have occurred, like the Tohoku earthquake or the Sumatra earthquake or the Great Chilean earthquake. So I hope this gives you a different perspective, or the true perspective, of what we mean by earthquake magnitude, what the differences in magnitude actually mean. So let's change gears a little bit and let's talk about sea level stations. Well, there are 3 basic types of sea level stations. There are the coastal sea level stations. These are typically situated in harbors, along piers, in shallow water. Then there are the darts, which are pressure sensors that are situated in very, very deep water, perhaps several hundred kilometers or more off the coast. And then there are cabled sensors, which are essentially pressure sensors, but they receive power and can transmit the data through cables that connect it to a device on shore. Now, there are very few cable sensors that we use, so I'm just going to spend most of my time talking about the coastal sea level stations and the darts. The coastal sea level stations, their primary function is detection. The first record of a tsunami will normally come from a coastal tide gauge, and it's our primary means of detecting a local tsunami. That is, a tsunami that will only affect the regions very close to where the earthquake occurred. They provide facts on the ground. They provide what is the impact information on the coast. And once a tsunami is declared destructive, it is the tide gauge readings that are used as the basis for canceling the warnings. In other words, we will use that to determine when the tsunami waves have decayed to safe levels. And at that point, we'll issue an all clear. And they're also a fail-safe in case our forecasts are an error based on the earthquake and the darts. So the dart stations, they're situated in very deep water. Their primary function is to help the warning centers to distinguish between tsunamis that will propagate across an ocean basin with destructive power from those that would just simply be measurable on sea level stations. Every unnecessary evacuation here in Hawaii can potentially cost the state $75 million. So if there's an earthquake on the Pacific Rim, we really want to be able to nail down whether it's going to be a problem in Hawaii or not. And likewise, we can use the DART stations to cancel any sort of warning. If we issued a warning watch bulletin and what shows up in the DART buoys is small, we'll then just cancel it. So the coastal sea level stations, again, they're situated in shallow water. They're typically installed along piers. They're the first normally to detect the tsunami. They provide us the facts on the ground, and there are lots of them. And basically the way they work, this is a sea level installation that we have out in Hiva-O and the Marquesas. It transmits the data via a geosynchronous satellite. That data is downloaded in Wallops Island, Virginia, and forwarded to the U.S. Tsunami Warning Centers and other meteorological offices around the world. The DART buoys work something a little bit similar, but here's the pressure recorder sitting on the bottom of the ocean in deep water, transmitting its data via hydroacoustic signals to the DART buoy, which transmits to an Iridium satellite. It's based on the Iridium system. And then that data is downloaded by the National Data Buoy Center and then also forwarded to the U.S. Tsunami Warning Centers. These are very exquisite instruments. They can measure fluctuations in sea level as small as 1 millimeter. So they're very exquisite instruments. And back in 2005, we had probably about 100 or so sea level stations distributed around the Pacific Basin. Again, this is the only place where there was a tsunami warning system at that time. And also there were about a half dozen DART buoys that had been deployed. The DARTs were something of a new technology in the early 2000s. Now, we fast forward to 2014. You can see now that there are literally hundreds of sea level stations around the world, and the DART network has greatly expanded. Today, there are approximately 60 or so DART stations operating around the world. And so the picture has brightened considerably in terms of the amount of seismic data we're now receiving and the amount of sea level information we're getting. Now, one of the things we can do due to advances in computational science, due to the advances in computational technology, we can actually generate what we call a real-time wave height forecast. And it's a model that was developed in-house by Dr. Dylan Long, and we call it RIFT. It basically requires the magnitude of the earthquake and what we know about the geometry of the earthquake and the location. And we can use that information to then calculate what the ground displacement resulting from the earthquake is, and then we can use that to generate a tsunami in a model. So this is the results of the RIFT model for the Japan earthquake that occurred in 2011. The forecast requires about 7 minutes to compute. And so this is what we obtained. Now, the scale indicating the expected size of the tsunami when it arrives on shore here, here's the amplitude, this color scale. And not surprisingly, these red and pink colors are going to be found in Japan, where closest to where the earthquake occurred. But you'll note that this tsunami will propagate all the way from Japan into Chile with destructive power. And in some places in Chile, the observed waves were as much as 3 meters. Okay? And so this forecast is actually fairly reliable, as it turned out. Now, we did this forecast. We didn't quite have this technology ready to go back in 2011, but it is operational now, and all of our message products are based now on a forecast, rather than just simply being based on the earthquake magnitude. So how does this forecast jive with all the observations? Well, if we plot the forecast amplitude on the left and plot that against the observed zero to peak amplitude at the tide gauges, we can divide this chart up into several sections. One thing I want to know is, did we fail to warn any place? And our criteria for issuing a warning to the state of Hawaii, for example, is 1 meter. And a lot of places around this world use this threshold. If you have a tsunami amplitude greater than 1 meter, then that's a possible inundation threat and could cause some damage and loss of life. So 1 meter is our threshold for evacuating the state of Hawaii. And we can see here that if we compare our forecast to the observations, there is no place in the Pacific that we really failed to warn, that we would have failed to warn had we used that forecast as the basis for issuing warnings around the Pacific. Likewise, there are very few places where we overwarned. That is, the forecast predicted amplitudes greater than 1 meter, but less than 1 meter was observed. Likewise, so as a result, most of the areas fall in these two categories. One is properly warned and properly not warned. So it appears that these forecasts can generate information that's useful to emergency management systems. We don't necessarily need to know exactly what the forecasted amplitude is. We just want to understand whether it's going to be dangerous or not, and that in itself is useful information. So this represents a major advance from what was available in 2004. So I'll finish up showing you some tsunami marograms. These are actual sea level records. This is recorded for the Chile earthquake back in 2010. This is Coquimbo in central Chile. You can see that the tsunami amplitude here is almost a little bit more than 1.5 meters. This is on a tide-corrected marogram, so the effects of the tides are removed. This is what we saw for Talcahuano. The station at Talcahuano was basically destroyed by the tsunami. It more or less got knocked offline after the second wave arrived. Here you can see in Coquimbo how the danger can persist for many hours. So this is about 8 UTC, and already here we're 6 hours later. We still have fluctuations that are potentially hazardous in Coquimbo. Tohoku marograms. The red curve is the actual marogram. The black is the tide-corrected marogram, where we remove the effects of the tide. The Ofanado sea level station was the closest to where the earthquake occurred, and that was knocked out by the earthquake. And then here in Hanasaki, which is further to the north, you can see here that the initial wave to arrive almost had an amplitude of close to about 3 meters, and oscillations persisted for many hours. The other thing is, that you can see here is that the period of these oscillations is on the order of tens of minutes. So that's a clue that this is going to be a problem as the tsunami moves across the ocean. Oops. This is the dart record from the dart that was closest to where the earthquake occurred. And here we can see an amplitude of almost 2 meters on the dart. This is the largest amplitude ever recorded on a dart. And when we saw this, we knew that the Pacific Basin was probably going to be in trouble. And in fact, the Tohoku tsunami did propagate across the Pacific Basin with destructive power. But there were very few casualties outside of Japan because we have a tsunami warning system in the Pacific Basin. And the tsunami affected places all across the Pacific. And here's a tsunami record from Acapulco in Mexico. And here you can see these oscillations growing in the harbor. The first wave here was not the largest. The oscillations resonated and grew over the course of several hours. And let's talk a little bit about the Meteor tsunami of June 23rd, 2013. A derecho traveled across the central United States, and when it got past the East Coast into the Atlantic, it actually generated a tsunami that was recorded on sea level stations in New Jersey. Here you can see the tsunami generated. It had an amplitude of a few tens of centimeters. Here in Virginia, also an amplitude of a few tens of centimeters. And it was even noticeable as far away as Bermuda, although by this time the amplitude was only a few centimeters. Now, even a tsunami of a few tens of centimeters can produce dangerous currents in harbors. And so there are 12 people that were injured by the tsunami. A couple of them almost drowned by it. And this tsunami was also recorded by a dart. This is a dart that's east of Montauk Point, Long Island. And here you can see the initial tsunami, what we call the direct tsunami, that traveled from the source directly to the dart. And later on, there's a reflection from the coast. And as you know, when a wave reflects off a solid boundary, for example, when a tsunami reflects off a solid boundary, the phase is inverted. So the phase was shifted, and it shows up the second time after reflection as upside down. And in fact, you can make use of this information here to determine where the source region of the tsunami was and other things. So at this point, I'm going to cut away, and I'm going to move to a simulation that was generated by Dailing Wang of the Meteor tsunami. So the derecho is going to travel across the United States, and as it moves into the shallow water of the near coast environment, it's actually propagating at approximately the same speed as long waves in shallow water. This causes an effect known as Proudman resonance. And so a little mound of water that's growing ever larger is getting pushed across the continental shelf. And then when it reaches deep water, it generates the tsunami. And that tsunami then travels further into the Atlantic and also travels back to the coast. And you see a lot of trapped energy is trapped along the coast. And so, you know, this tsunami was rattling around in the coastal environment for some time. And this simulation is going to finish up with the coastal forecast, coastal amplitude forecast. This is more of a deep water forecast. And it's going to finish up with the coastal forecast in just a minute. We're almost there. There we go. And in some places, the forecasted tsunami amplitude was as much as a meter. Now, I don't think that was observed, but certainly a few tenths of centimeters was. And so this forecast actually, based on some very simple modeling of what the derecho was actually fairly reliable. So let me go back to the presentation. I'm just going to throw up this one last slide. These are some links where you can find some more information. Dylan Wong and Nathan Becker have collaborated on a number of simulations that you can find on our YouTube page. The National Geophysical Data Center has all sorts of information about tsunamis. There's also the National Warning Center, National Weather Service Tsunami Portal. And you can follow both the Pacific Tsunami Warning Center and National Tsunami Warning Center on Twitter and Facebook. And it's been my pleasure to give to you this presentation today, and I'll entertain questions. Thank you very much.
Thanks, Stu. That was great. A lot of folks sending in questions right now. So if you have a question, we've got about a half an hour to go over and answer some of these. You did mention there the Atlantic tsunamis, and when we talked yesterday, you had brought up some interesting cases. Lisbon in the late 1700s and
Yes,
Labrador 1920s. Can you talk about those just for a minute?
Yes. The Atlantic Ocean, fortunately, is not ringed by subduction zones like the Pacific. So the threat of earthquake-generated tsunamis is much less for, let's say, the East Coast than anywhere else in the Pacific Basin. But nonetheless, there are earthquakes that do occur in the Atlantic. And in 1929, there was the Grand Banks earthquake that occurred off Newfoundland. It resulted in a tsunami that killed 60 people in Newfoundland. It generated potentially destructive waves in the northeast United States, such as along the coast of Maine, but it did not kill anybody outside of Newfoundland. And that was in 1929. In 1755, there was the Great Lisbon earthquake. Seismologists today, on the basis of historical records, based on the damage that it did, believe that that earthquake may have had a magnitude as much as a 9. And it most certainly would have sent destructive waves into the Caribbean, into the east coast of the United States. And there's potential for an earthquake like that to occur again. And so the Atlantic coast does have a threat. It has a threat from earthquake-generated tsunamis. It's minimal, but nonetheless, it's still there. There still needs to be a warning system for the Atlantic. And of course, as we saw, that there is the potential for meteor-tsunamis to generate tsunami hazards along the east coast of the United States. So the east coast of the United States falls under the jurisdiction of the National Tsunami Warning Center in Alaska, and they are in the process of developing all of the communications with the emergency management systems on the east coast.
The Haiti earthquake there in 2011, did that create any tsunamis in the Caribbean?
Yes. Well, yes, it did, but it was a local tsunami.
Okay.
It basically more or less just affected Haiti, and there were some measurable waves recorded in the Dominican Republic. It actually generated a tsunami that had an amplitude of about 1 meter, so just to the south of Haiti. So it actually did generate a tsunami. I don't know to what extent that tsunami caused damage or hurt anybody, but given what the earthquake did, it was probably of minor significance compared to the damage and devastation wrought by the earthquake itself. And that occurred actually in January of 2010.
Oh, okay, thanks. Hey, we've got a lot of questions coming in. I've got another one here for you, and this is kind of related. Two of these. Thomas writes in, and he says, say you have a 50-foot tall tsunami, 50-foot tall wave, I guess, coming, or this whole tsunami coming to the beach. We don't want to call them waves. What altitude do you need to be at to seek avoiding being impacted by the wave? So, two questions, that, and the other one I had was, if you are swept out in a tsunami, what should you do? So, could you answer those?
Well, how high you should get? You should probably get at least a factor 2, and then for sure you'll have nothing to worry about. So you want to make sure you're at least twice the wave height, but you also want to make sure you're inland. So really, the object here is get inland and as uphill as high as you can get as quickly as you can get. No point in taking chances. On flat areas, even a tsunami that maybe only has an amplitude of a few meters, it can inundate for better part of a mile, depending on how flat the land is, depending on what the period of the tsunami is. So yes, the advice I give to people is just head inland and uphill as quickly as possible. Don't look back until you get the all clear. Worst that happens is you've taken a long walk for nothing. On the other hand, it's a type of action that could very well save your life. So I would try to fine-tune things based on what the size of the arriving wave is. Get out of harm's way. With respect to the second question, if you're swept out to sea by a tsunami, well, first rule is do not get swept out to sea by a tsunami. If you do, the thing that I would try to do is find something that you can float on. Some debris, a piece of wood, a tree or something that's dragged out. Try and hang on to that. Do not try to swim. Do not try to fight the current. Do not try to go back to shore. Just hang on to something for dear life, and hopefully you'll be found. But if you find yourself in that situation, there's very little you can do.
Thanks, Stu. Here's a question from Joe. He wanted to know that, in the ocean as it moves along, called a tsunami, is there a different name once it comes on shore? Is it still called a tsunami? His question.
Yes, we still refer to it as a tsunami.
Okay. Here's another one, and Tom writes that his dad was an officer in the U.S. Coast Guard, and geodetic survey back in 1959. There was I guess a earthquake off of Chile, and he was in Hawaii. He issued a warning for Hawaii, but the warning, nothing happened. He said that was the hardest decision of his career. So issuing these warnings, Matthew writes in, related, so he said, how is the $75 million cost calculated for Hawaii? He said, it seems like a lot of money just to tell people to go to higher ground. So I guess maybe you can relate these questions.
With the cost is, it's not simply people going to higher ground. Emergency responders have to be mobilized in case the people are getting hurt. The police are out in full force. They have to set up roadblocks to make sure traffic flows the way it's supposed to. The civil defense agencies are spinning up, getting all their people into the office. So there's a lot of people that are involved. It's not simply people getting up and leaving their houses. Now if there's a local earthquake here in Hawaii, for example, a great earthquake occurs in Hawaii, well, we don't have time for an orderly evacuation. It's just a couple minutes at best, warning that we can give, and then at that point, what people really need to do under that situation is just head inland and uphill as quick as possible. But for the situation where we have a great earthquake occurring on the Pacific Rim, we have several hours to act, and we can conduct an early evacuation so that nobody gets hurt, nobody gets left behind. and that requires a fair bit of resources to do that. And hence, that's where the price tag comes from. Also, businesses have to close down, and so there's loss of revenue and stuff like that. So it's not a trivial matter.
Thanks, Stu. Here's another question that comes in. The lady Debbie lives in Crescent City, California, and she says that Northern California seems to get hit hard a lot of times by these tsunamis. Could you explain why? There's a lot of damage in 1964 and 2012.
Sure. Well, Crescent City is a very famous location for tsunamis. It's well known for the Crescent City tsunami that was generated by the 1964 Alaska earthquake. And that tsunami propagated up the Crescent City River, causing a lot of destruction. Now, Crescent City Harbor is actually, its fundamental period is similar to that of many tsunamis. So when a tsunami enters Crescent City, there's a strong resonance. And so that harbor amplifies the effects of the tsunami. So while other parts of Northern California may not have much damage or see very large waves, Crescent City often will. And so it's unfortunately special in that regard.
Here's a message, a question from Gary, and he says he's heard that there is a geological formation in the Canary Islands has a potential to cause an enormous tsunami, something like an enormous landslide. And also another question had come in here from Stu, was saying that there's he saw on the Discovery Channel a few years ago a program about mega tsunamis, about a chunk of the Big Island sliding off, with the mega tsunami reaching 1,000-foot elevations in Oahu. Are these things possible? So maybe two separate questions here. One of the Canary Islands one, and then the Hawaii one.
Well, yes, they are possible, and we have pretty good evidence that, in fact, they have occurred. So it's not really a question if they're possible. It's sort of a question of when the next one is. Fortunately, these events are very rare. They may occur only once every few tens of thousands of years, and that's a good thing. There are people that are concerned about La Palma in the Canary Islands. This is one of those volcanic islands that possibly could collapse, and it can generate an intensely destructive tsunami in the vicinity of the Canary Islands, probably adversely affect the coast of Africa. Now, to what extent it'll affect the East Coast of the United States, it'll probably send somewhat damaging waves to the East Coast of the United States, but it's not going to be anything scary like the 200-meter wave or something out of the movies. Fortunately, if there is one saving grace for these types of landslide-induced tsunamis, it is that the mechanism that generates it has a very small length scale. And even though these tsunamis are extremely large, they have very large amplitudes, their wavelength is actually fairly short. And so what that means is that as they propagate across the ocean, they're going to experience a phenomenon called dispersion. And so these intense short period waves, they're actually composed of a number of different components. A number of different, they have a spectra. And the individual waves that make up the spectra, they move at slightly different speeds. So as that terrible wave is going to move out into the ocean, it's going to get knocked down. As its individual components start traveling at different speeds, it's going to spread out. So by the time it travels 1,000 kilometers or so, it's not going to be so nasty. But if you're in the near field, relatively close by to one of these mega tsunamis, it's going to be very bad. But far away, not so much. And similar thing is true with meteorite impacted tsunamis.
Stu, you mentioned about the movies there for a second. Do you have a favorite with tsunamis? I know The Impossible came out a couple of years ago. Is there one that would be interesting for folks to watch?
Well, there's Deep Impact and Armageddon. They both came out, I think, in the late 90s. Those are two of my favorites.
Okay, thanks. Here's a question coming in from Ron, and Ron wants to know, can an inland earthquake generate a tsunami warning for islands offshore?
Well, it depends on how far inland. I mean, if you have a great earthquake and it's just a few tens of miles inland, You know, like if you have like a 9.0 and the epicenter is like 30 miles inland, that's probably not going to be a big deal. That will still likely cause the displacement of the seafloor and generate a tsunami. Now, if you have a big earthquake and it's like, you know, in the middle of Siberia, I don't think you have anything to worry about. So it needs to be relatively close to the shoreline.
Okay, here's a question. Henry writes in, and also we have another one here about space objects, meteors and stuff causing tsunamis. Could you elaborate a little more on that? Is it a similar type of thing?
Yeah, I mean, periodically, you know, the Earth is going to get hit by large meteorites, and if they land in the ocean, they will generate a tsunami. Now, locally, it might be pretty intense, but again, the effects of dispersion will quickly knock down the size of those waves, so that by the time that tsunami moves, you know, 1,000 kilometers or so, it's going to be relatively harmless. Of course, meteorites come in all sizes too, and if we're talking about something that, you know, was the size of the meteorite that struck the Earth that caused the end of the Cretaceous period, that's a different ballgame, and something that massive, that large, could generate a massive tsunami that could travel across an ocean.
Matt writes in, and he was wondering if it would be possible to get a link to that animation on the earthquake magnitude that you're showing. He thought it's a great teaching tool for students, and if you can send that, we can put that up on our website as well. So, if it's possible to show that.
Look for our YouTube page.
Okay.
I have showing.
Yep.
You'll find pretty much all the videos that we've done at P2WC on the YouTube page.
Oh, super.
Feel free to friend us on Facebook and join us on Twitter.
Great. Hey, here's two questions coming in. Actually, Randall and both John asked similar questions. They're surprised for the 10% of all tsunamis are unknown. And is that because the field of studying technology is relatively young, or maybe there's not enough tsunamis each year to study and collect data? So they were wondering about that, the unknown.
Well, yeah. Well, some of these are historical tsunamis, and you know, that was before there was any sort of seismic instruments or sea level monitoring devices or things like that. So we're not quite sure what caused them. You know, it's just as simple as that.
Okay, Jim in New York writes, and he wants to know, based on your studies, are tsunamis increasing in frequency?
Oh, you know, I don't think so. I mean, the era of sort of modern tsunami science and modern seismology is only about a century old, and you know, the Earth has been around here for 4.5 billion years. It's hard to know whether a 100-year sample of the frequency of tsunamis tells us anything meaningful with respect to what's been going on for the last million years. What I can tell you is that certainly, if you go through the database, you'll find a lot more. You'll find information on a lot more tsunamis that have occurred in the 20th century than occurred in the 19th or 18th century. This is because, you know, we have sea level stations, and so a lot of tsunamis that have gone unnoticed because their amplitudes were small won't go unnoticed today, because, you know, sea level stations and the darts will measure them, and they'll find their way into the database. So no, I don't see anything that would suggest that the frequency of tsunamis is increasing.
Okay, we got a couple more minutes here, and you know, it's funny. You see pictures of tsunamis all the time, and they seem to be in the daytime. Maybe I'm wrong on that. Is there any? I know there should be no correlation, but have you found any correlation? It's probably more helpful for people if they're in the daytime than if they come at night. Any comments on that?
Well, you know, tsunamis can occur any time of day. There's no tsunami season, so they occur whenever. Now, some people, you know, as the tsunami makes its way across the ocean basin, it's going to go through a lot of time zones. So So for some people, they will have the tsunami waves during the day, but that same tsunami will interact with other coastlines where it's night. That was kind of the case for the Chile tsunami back in 2010. It struck in the early evening in Hawaii, but by the time the tsunami waves got to Hawaii, it was the early morning. And in Chile, of course, it was when the earthquake and tsunami struck, it was the middle of the night. So no, it makes no difference. Daytime, nighttime, time of year.
Stu, if you have a NOAA weather radio, would an alert go off on that for a tsunami coming your way? Is that something that's...
Yes.
Okay, so
Yes,
folks, if you have those...
Our the NOAA weather wire, and those were supposed to be relayed over the weather radio. Not only the weather radio, but the emergency alert system will also carry information about a tsunami warning.
Okay, so if you're sleeping in the middle of the night,
that header will pop up, or trailer will pop up and says tsunami warnings in progress, that kind of thing.
Okay. We're going to try to get to a couple more of the questions here. We have a question that has come in from Matt, and he says, you mentioned that coastal stations are the first one to record tsunamis. How do they work exactly? Do they record the seawater that recedes at the shoreline before coming back as a tsunami wave? How does they work?
Well, they just measure the changes in the sea surface. So as the water moves up and down, they will track that. So whether it's coming in or the ocean's receding, they will track that. Now there are a number of different types of ways to do this. One is a pressure sensor. So it's just a little pressure sensor that sits on the seafloor, and as the water comes in, as the tide, let's say for example it's high tide, it's going to exert more pressure on that sensor, and that's going to be translated as an increase in sea level. Likewise, when the water recedes, that's going to be result in a decrease in pressure, and that's going to be translated to a decrease in sea level. So the pressure sensors are the easiest ones to understand.
Okay, great. Here's Richard in Oregon wants to know if we have a Great Cascadia quake, what is the estimated time for coastal Oregon? And it would go out and well, Cascadia quake, would that be offshore? I'm not sure.
Yeah, it would be somewhat offshore. I mean, I don't know offhand exactly how much time it would be before the damaging waves got to the coast. I'm guessing, offhand, I'd say perhaps from 10 to 20 minutes. But that's highly variable. The National Tsunami Warning Center, they're very good at what they do. They should get out a warning perhaps in 5 to 10 minutes, probably more like 5 minutes. Within 5 minutes, it's difficult to determine what the true size of the earthquake is, but they will have an understanding that it's a very big earthquake, and they will issue a warning fairly quickly.
Okay, John writes, and he says that the Great Lakes have been subject to a few large waves that have killed people who that there was no warning. Is that what government agency is responsible for studying and alerting for that type of activity? And I don't know if those are earthquake-induced or what on that.
Yeah, I suspect those are probably results of storms. I'm guessing maybe the National Weather Service may have, if it's going to be storm-induced, possibly the National Weather Service may have some responsibility for that, but I actually don't know.
Okay. Yuli writes and wants to know about tsunamis generated by volcanic activity. Flank collapse, etc. El Viejo is said to carry that danger. Could you talk about those?
Yes. Well, it's basically the situation that's going on that we're worried about in the Canary Islands. So basically, you have to remember that these volcanic islands, they're just big piles of rock, mostly basalt. And they're piled up so high that, in fact, the strength of the rock is unable to support its mass. The Big Island of Hawaii is actually the largest mountain on Earth. It's just that only 14,000 feet of it are above sea level. whereas all of Mount Everest is above sea level. But if you would include the part of the Big Island that's below sea level and add that to that 14,000 feet, you get something that's on the order of like 35, 36,000 feet. That's a big pile of rock, and it can't support itself. So what happens is these volcanic islands, they're in tension. They want to fall apart. And as a result of this tension, they are ringed by faults, tensional faults. And every so often, perhaps every few tens of thousands of years, one of these tensional faults are going to become very active, and a large chunk of that island is just going to slide off. That's how these islands collapse. They are eroded away, but they also suffer periodic collapse, and that's how they diminish. This is why if you go westward along the Hawaiian Islands, they get successively smaller. The islands themselves get successively smaller, and their maximum elevations get successively smaller. And finally, as you get further down the chain, you don't find very many of the, you don't find very, they're basically just seamounts because they're no longer extending above the surface, and this is due to erosions and these collapses.
Jerry writes and asks, how did the Derecho cause the tsunami that you showed? Was it an abrupt pressure change? Was it wind? What was the help?
It was the pressure change. As far as I understand, it's the pressure change. Yeah, the wind isn't really going to whip up a tsunami, but the pressure change, and it coupled with something called the Proving resonance. So for you folks listening, my homework assignment for you is to look up what the Proving resonance is.
Okay. We have a couple more. Do you have a minute or two still left, Stu? Are you okay?
Sure, absolutely.
Okay. Warren writes in, and he wants to know, he says that the Japanese tsunami a couple of years ago seemed to come in as a fast-moving wave, while in other cases, including the Indonesian tsunami, was manifested as a rapid rise in water level. Why the difference?
Yes, that's a very good question. The same tsunami can appear very differently in different places. And that has a lot to do with what the nearshore topography, the nearshore bathymetry is like. Depending on what the nearshore bathymetry is, the wave can show up as a sort of like a tidal bore, a very steep-faced wave, or it can just show up as a rapidly rising tide. And that kind of depends on the nearshore bathymetry. If it's a fairly gentle sloping, if you have a very gentle sloping coastline that then falls off very rapidly at some point, when that tsunami interacts with that shallow water, it's going to slow down in a hurry, and that's going to result in something like a tidal bore. In other cases, it'll just appear as a rapidly rising tide.
John is asking about what extent does the topography of the seafloor near the shore affect the height and inundation levels of tsunamis? Is it negligible? One example might be Monterey Bay Canyon off the coast of Central California.
Well, sure. The nearshore bathymetry can have a very, very strong effect, and certainly the shape of the harbors, the bathymetry in the harbors, these effects are not trivial, and in fact greatly affect the tsunami because of resonance effects and other effects. They can exert a huge influence on the character of the tsunami. That's
Georgia.
one of the reasons why we put in the darts. If I can just, one of the reasons we put in the darts is because we wanted to understand what the tsunami was like, unfettered by all these coastal resonances and all these effects of nearshore bathymetry. So by putting these pressure sensors, these dark buoys in deep water, we can actually see what the tsunami is like in deep water where it's unfettered by all these resonance and nearshore effects.
George from Buffalo actually has a question on the darts, and also he had asked if we can provide a link, and is that to the dart technology? Is that on your on the web page there, the list of things?
I think if you go to the tsunami.gov, I think you'll find a link to the National Data Buoy Center.
Okay.
www.ndbc.gov.
Okay.
And the National Data Buoy Center, they're in charge of maintaining the DART network for the United States.
So his question was that they sit on the ocean floor, read pressure at 5,000 feet below the surface. He's saying the pressure would be huge, and can this determine a change of 1 meter, and how is it different from normal waves passing by? So is removing the noise from the events, is that difficult?
Yes, yeah, exactly. It's a very good question. I was waiting for somebody to ask this. In fact, not only can they measure a 1 meter wave, they can measure a 1 millimeter wave. And people are like, really, 5,000 meters beneath the surface, you're going to detect a change in sea level on 1 millimeter, really, Stu? How does that work? Well, the fact of the matter is, one of the things you get, another thing you get by putting your pressure sensor in deep water, one is, of course, as I mentioned earlier, it's not going to be affected by coastal resonances. The other thing is that the thickness of the water column acts as a natural filter, which is something that Henry was getting at. It acts as a natural filter. So for all those waves that you see on the surface, like the ripples and the sea swells that make you sick, their pressure disturbances don't extend all the way down to the bottom of the ocean. Their pressure disturbances basically fall off exponentially as a function of their wavelength. So if you have a swell that has a wavelength of 100 meters, by the time you're about 300 to 400 meters down, the pressure disturbances associated with that swell are going to be negligible. And so by the time you where the dark buoy is, by the time you're where the dark pressure sensor is, the only disturbances that are going to produce pressure changes that will be sensed by the dark will be pressure changes due to the tides and due to the tsunamis. Only the very long waves are going to have pressure sensors that are sensed by the dark. And it's those sea level changes due to those kinds of waves, that's all that we're interested in. So it's great. It filters out the stuff that we're not interested in. It just shows us the stuff that we are interested in. Works out wonderfully.
Well, Stu, we're going to take one last question here, and again, thank you for taking time out of your busy day to be with us. Charles writes in, and he wants to know who studies past tsunamis in the geological record. So who's out there studying that? That field? Yeah.
Oh, there are a number of people. Brian Atwater is one of the prominent U.S. scientists that studies historical tsunami deposits. Also here at the University of Hawaii, one of our duty scientists, Gerard Fryer, is also, and his colleague at the University of Hawaii, Gary McMurtry. Yeah, no, there are a number of scientists that are very interested in looking at paleo-tsunami deposits. And so it's a vibrant field, it's alive, and it's not thousands of people doing it, but there are a couple dozen good people that are very interested in that.
Well, Stu, thank you so much again for being with us today. This is great stuff. We're going to put all that information up on the webpage. We will post, if you go to our WeatherTalk webpage, we'll have a specific one here for this webinar today with all those links. And I appreciate again you being with us today. So, folks out there, if you would mark your calendars, we have another special webinar coming up next Thursday. We usually don't do 2 a month, but this is one on Thursday, December 11th at 1 p.m. Eastern Time. It's going to be a review of significant weather events occurring in 2014. And if you were with us last year, Greg Carbon of NOAA's Storm Prediction Center puts this together. Really a fascinating look at the top 10 events that occurred in the year. And we will have that. So if you go online, you can register for that, and that should be a great one. And finally, everyone, when signing off today, please take the survey that'll pop up on the screen. If you'll do that, that'll help us and our evaluators know how we're doing with these webinars. So on behalf of the CoCoRaHS team here and the Colorado Climate Center, until next time, this is Henry Regis saying thank you again, Stuart, and to everyone out there, have a good afternoon, and we'll see you next time. Bye-bye.